To calculate the exact likelihood of any event, we start with a strict ratio, the number of specific target outcomes divided by the total number of possible outcomes in the system. In a finite uniform sample space, an event is simply a specific subset of those possibilities. Look at these two distinct vintage coins, a quarter and a dime. If we toss them, we are evaluating a microscopic sample space. With just two coins, we can manually map out the entire system. Heads, 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 tails, tails, heads, tails, tails. 4 possible outcomes, easily counted by brute force. But the moment you add more variables to a system, the ability to count manually fails. The sample space does not scale linearly, it expands geometrically. We can see this scaling problem clearly in the Canadian 649 lottery. This diagram illustrates the mathematical reality of that system. Drawing just 6 specific numbers out of a pool of 49 generates nearly 14 million distinct possible combinations. You cannot map 14 million data points by hand. To navigate a system this large, we rely on combinatorics, the mathematical logic of counting without enumeration. By building a combinatorial counting engine from first principles, we bypass brute force counting entirely, allowing us to map massive state spaces with exact precision. The baseline combinatorial action is taking a specific number of distinct objects and arranging them into a strict sequence. This decision tree maps a 3-letter set, A, B, and C. We use n factorial as our baseline multiplier. Following the branches down, we count exactly 6 terminal pathways. The math confirms the visual. 3 choices times 2 times 1. 3 factorial equals 6. This assumes we are choosing without replacement. Once an object is pulled from the pool to form a sequence, it is removed from the available options. Selecting an ordered subset called K, smaller than our total pool n, requires an adjustment, the permutations equation. P of n comma k equals n factorial divided by n minus k factorial. On the tree, that denominator acts as a scalpel, mathematically slicing off the unselected lower branches. Calculating permutations is an exercise in subtraction. We establish the maximum theoretical pathways and then algorithmically prune away the branches we do not traverse. Our counting engine hits a complication when the objects in our total pool are not unique. This visualizes a 5-object set, 2 A's, 2 B's, and 1 C. Notice the slight differences marking the identical letters as separate objects. If we treat these 5 objects as individuals, 5 factorial gives 120 arrangements, but that number is artificially high. Swapping the physical positions of the A blocks does not change the sequence's actual data. It still reads AABBC. To correct this, we use the logic of the multinomial theorem. We divide the total factorial space by the factorials of the identical subgroups. Applying this to our set, we take the 120 total paths and divide them by 2 factorial for the A's times 2 factorial for the B's times 1 factorial for the C. The real number of unique permutations drops to 30. Identifying identical subtypes is a critical parameter to prevent inflating our sample space with duplicates. We now shift the operational condition from ordered sequences, permutations, to unordered sets, known as combinations. In a combination space, the specific chronological sequence of selection has no mathematical weight. Only the final grouping matters. This animation shows our permutation equation morphing into the combination formula, CNK, by adding an extra k factorial factor into the denominator. This extra division performs a specific mechanical task, collapsing differently ordered sequences containing the exact same items down to a single state. If we select letters A and B, the distinct permutations of AB and BA collide and fuse into one unified combination. Combinatorial logic is a structural property of mathematics. It applies to abstract variables just as effectively as physical objects. As this visual shows, these exact combinatorial ratios naturally mirror the coefficients we see when expanding algebraic binomial and multinomial polynomials. Whether expanding an abstract equation or counting lottery tickets, combinations cleanly calculate the absolute size of unordered spaces. This photograph of a live game grounds our final application. We will apply our combinatorial framework to solve a 5-card poker hand. Our target event is being dealt a full house, which requires exactly 3 cards of one rank and 2 cards of another. Choosing 5 cards from a 52-card deck yields 2,598,960 possible hands. For the numerator, choosing 2 ranks out of 13 gives 78 rank pairs. Selecting 3 suits for our triple yields 4 combinations, and 2 suits for our pair yields 6. Using the multiplication principle, we multiply these factors together. 78 ways to pick ranks, 4 ways to suit the triple, and 6 for the pair. However, within any pair of chosen ranks, like kings and fives, there are 2 distinct ways to build the hand: 3 kings with 2 fives, or 2 kings with 3 fives. To account for both configurations, we multiply our suit combinations by 2, bringing our total to 48 combinations per rank pair. This results in exactly 3,744 distinct full house hands. By dividing the 3,744 target states by the 2.6 million total sample space, we find our precise probability. Incalculable odds are calculated through combinatorics.
Knowledge is power, boy. Like, subscribe, and prepare for the next battle.